This time I want to talk about a way that you can use all this stuff about extrema and concavity and increasing and decreasing, everything that we've been doing for the past while now. You can use all that stuff actually as a general purpose way to draw the graph of functions. You probably learned at some point in your life how to say draw the graph of a line. You might have learned how to draw the graph of any parabola, but I'm talking about any function you can think of. This method that we're going to talk about can actually be used to sketch the graph of pretty much anything as long as you're capable of understanding the derivatives. So this section in the book is called Curve Sketching. Just a little heads up, these problems are probably the longest ones that we're going to do all semester. That is, a single curve sketching problem will require a lot of effort. It's not that hard, there's just a lot of steps to go through to do it. Anyway, let's curve sketching, all right? I think we should just go for some examples here. Here's my first example. Sketch the graph. Sketch the graph of this function here, x to the 4 minus 8x to the 3 plus 18x squared. Anyone just know off the top of your head what this looks like? No, there's no reason you should know what that looks like. Here's the idea though. We're going to take the derivatives, find all the critical numbers, find all the inflection points, make some charts about where is it increasing, where is it decreasing, where is it concave up, where is it concave down. And once you compile all that information together, it turns out that's actually enough information to just draw a picture of the graph. So let's, how exactly to do that, we'll get to eventually. Let's start off by taking the derivative and taking the second derivative, just because we're going to have to use those eventually. The first derivative, in this case, these are easy to do. 36x, right? That's the first derivative. The second derivative, 12x minus, we got 48x plus 36. Okay, there's the two derivatives. Let's begin by doing the chart for increasing and decreasing, all right? I guess actually the first thing would be find the critical numbers. All right, to find the critical numbers, let's simplify this as much as we can. You can factor 4 out of all of this, right? 6x squared plus 9x. Next, you can factor x out of all of there. So it's actually 4x. I guess I could have done that all in one step. X squared minus 6x plus 9. And now this factors. And you get x minus 3 and x minus 3. Okay, so this is the fully simplified version of the first derivative. Maybe I'll put that up here. 4x times x minus 3 squared, right? Okay, to find the critical numbers, I want to say, when does this not exist? The answer is never. This always exists because there's no denominators or anything. Also, when is this equal to 0? That is something that we should actually check. So f prime equals 0. When? When this equals 0, or that? When that is 0, 4x times x minus 3 squared equal 0. Okay, I got things multiplied to be 0. That means one or the other is 0. This is 0, or x minus 3 squared is 0. Okay, that means x equals 0, so this is one critical number. Over here, you square root on both sides, you get x minus 3 equals 0, and then you add the 3, x equals 3. So this is my other critical number. Okay, let's do the old increasing, decreasing chart. My two critical points were 0 and 3. These were points where the first derivative was 0. We need to plug in intermediate points to check the signs of f prime of x. So let's try f prime of, back here, let's say minus 1. What's it going to be? 4 times minus 1 times minus 1 minus 3 squared. This is 4 is positive, minus 1 is negative, and this is positive. Actually, this part is always going to be positive because it's something or other squared, and anything squared is positive. So this whole thing is a negative, all right? Next, let's use 1, f prime of 1. 4 times 1 times 1 minus 3 squared. These are all positive, right? This one is still positive because it's being squared. So there's a positive there. And f prime of something bigger than 3, how about 4? 4 times 1 minus, not 1, 4 minus 3 squared. Again, these are all positive. So this is positive. All right, so as far as increasing or decreasing, it's decreasing here, then increasing here, then increasing here. Okay, that was the first derivative, increasing and decreasing stuff. Let's do the concavity stuff. So all the same steps, but using the second derivative instead of the first. Let's do that. Okay, from the previous steps, we already found this, the second derivative. Let's simplify as much as we can. And eventually we're going to have to set this equal to 0 and factor as usual. So 12 can factor out. X squared minus 4x plus 3. And now this right there can factor x minus 3, x minus 1. All right, so this is the second derivative. We want to find points where this is 0 or where this does not exist. Again, does not exist is not an issue here because there's no denominators or anything. There are places where the second derivative equals 0. However, set this equal to 0. 12, x minus 3, x minus 1 equals 0. Solve for x. The 12 doesn't matter. You can divide it away. These guys, the product is 0. So you go x minus 3 is 0 or x minus 1 equals 0. X equal 3 or x equal 1. These are my inflection points, or at least perhaps they are inflection points. These are where the second derivative is 0. Okay, let's make that chart for concavities then. All right, I want to know where is it concave up, where is it concave down. You make this chart here. 1 and 3 are the points where the second derivative is 0. Let's plug some points in between and see what happens. How about f double prime of, how about 0, right? That's the best point to use to the left of 1. Go up here, plug in 0. You get 12 times 0 minus 3 times 0 minus 1. Positive, negative, negative. So this is a positive. Concave up right there. All right, let's try 2. Would be in the middle between 1 and 3. F double prime of 2 is 12. Not x. I'm plugging in 2 for x, so it's going to be 2 minus 3, 2 minus 1. And what you get? Positive, negative, positive. So this is negative. And the last one, over here, 4. F double prime of 4. 4 minus 3 and 4 minus 1. These are all positive, so this is positive. Okay, that's my chart. I'm going to combine this with the previous chart that we had because you really want to see them kind of together, or at least next to each other. Here's a chart that combines the increasing, decreasing stuff and the concavity stuff. The first derivative chart, I'm going to write this slightly differently just because it's I think a little easier to read when you write it this way. The first derivative was the special points were 0 and 3. And we decided that this function was decreasing, then increasing, then decreasing, right? The chart for the first derivative was negative, positive, negative, and that means decreasing, increasing, decreasing. All right, and the second derivative, the special points for that one were 1 and 3. And notice I'm trying to line them up here, right? So 1 is to the right of 0, and 3 line up. And for this one, the second derivative, we decided it was positive, negative, positive. So in terms of concavity, that was concave up, concave down, concave up. And I messed that one up. Should have said increasing over here. Sorry about that. I heard that. Okay. So this is our sort of a double chart. Now the next step, we're actually ready to start drawing our graph right now. What we want to do is start. You can start drawing your graph sort of somewhere else on your paper. There's still a lot of steps to go, but you're ready to start drawing in any case. So I'm going to start drawing over there. Over here with the pink pen, let's start to draw the graph. What we want to do is plot these special points. So plot the x and y values for the special points. And by special, I mean, these points here, 0, 1, and 3. The special points, that is to say the critical numbers and the inflection points. All right. These are the x values. The x values are going to be 0, 1, and 3. What about the y values? How do you get the y values if you know the x values? For that, you use the formula. So to get the y value, you plug in to the original formula for this function, which we haven't used ever since the very beginning, but it was f of x equal x to the 4 minus 8x cubed plus 18x squared. Right? This is how you're going to get the y values. Each of those x values you're going to plug into this formula, and that'll tell you the y values. And I want you to plot those. There's going to be 3 points. All right? That's how we start making the graph. All right, we're going to plug these x values into this formula. So let's start. This will be the easiest one, I think. F of 0 is 0 to the 4 minus 8 times 0 cubed plus 18 times 0 squared, which is 0, 0, 0 all the way across. All right? F of 0 equals 0, so that means there's a point x equals 0, y equals 0. On your graph, you can indicate the point x equals 0, y equals 0. Just put a spot on there, all right? X equals 0, y equals 0. That's my favorite point, isn't it? Okay, next point, f of 1 is 1 to the 4. Plugging in down here again, 8 times 1 cubed plus 18 times 1 squared. All of these powers of 1 are 1, so this is 1 minus 8 plus 18. This is negative 7 plus 18 is 11. All right, let's put this on our graph. X equal 1, y equal 11. You don't really have to mark off all the little points. Just put 11 there, right? 1. Okay, last point to plug in, f of 3. This is going to be a bit of a pain, I guess. 3 to the 4 minus 8 times 3 cubed plus 18 times 3 squared. This is kind of a pain. Here's a little trick. Let's factor out a 9 from all these. These have high powers of 3 in them. If we factor out 3 squared from everything, what remains is 3 squared minus 8 times 3 plus 18. This is a little easier to do by hand. If you want, you can just plug all that into your calculator. Anyway, that's 9. 9 minus 24 plus 18. What is this in the parentheses? 9 minus 24 is negative 15 plus 18 is 3. So this is 9 times 3, which is 27. All right, so put this point on your graph. X equals 3, y equals 27. X equals 3, y equals 27, which is like up there somewhere. Okay, now is the time to connect the dots. We are almost done here. Connect the dots. Now, how do you tell what the curve looks like? Of course, you don't just connect them with straight lines because that would be wrong, all right? It has a curviness to this curve. How do you tell what kind of a curve shape is going to happen in between these points? The way is you look back at the increasing, decreasing, and the concavities chart, all right? And here's a little sort of quick reference here. I don't know if you need to memorize these pictures, but it can help to have this written down somewhere. If you have, say, increasing or decreasing or concave up or concave down, if you know the increasing, decreasing, and if you know the concavity, then you can tell what the picture has to look like. A curve which is increasing and concave up looks like this. A curve which is decreasing and concave up looks like that. A curve which is increasing and concave down looks like that. And a curve which is decreasing and concave down looks like that. All right, so let's look back here. All right, to the left of 0, what shape does the curve have? Go back and look at your chart. What happens to the left of 0? To the left of 0, your function is decreasing and concave up. That's what this chart says. Okay, he said decreasing and concave up over here, so it has to look like that. right? That's what such a curve looks like. So draw your curve like that. What about in here? Between 0 and 1. Go back, look at that chart. In between 0 and 1, your function is increasing and concave up. Between 0 and 1, it is increasing and concave up, which must look like that. Like so. All right, what about between 1 and 3? Look at the chart. In between 1 and 3, your function is increasing and concave down. Between 1 and 3, it is increasing and concave down, which has this shape to it. And finally, to the right of 3, for all points greater than 3, it is increasing and concave up, which has this shape. And that's the picture of the graph. We have sketched the curve. How about that? All right. It's a pretty cool method. I think there's a lot of steps to it, but it's kind of like a collection of all the stuff that we've been doing lately. And I always felt like this is kind of neat how you could actually figure out the graph of basically any function you can imagine as long as you're capable of doing those derivatives. Pretty cool, I think.